Hello and welcome to the first video on my channel Physimathizer. Here I'll be uploading math and physics videos about some of the topics I find most interesting in these fields. The content will range through middle school, high school and up to university level physics and math, but I'll try as much as possible to keep the content accessible to everyone without assuming any previous knowledge, because math was never about going to universities or studying. Since the days of Euclid, math was always about thinking and pondering. So, without further ado, let's jump right into today's video. The idea of this video came to me because I couldn't find any content that explains this fact, despite the popularity of our heroes today. Our protagonist is gonna be the Fibonacci sequence, and his sidekick is the infamous golden ratio. So, here's the deal. The ratio between two successive terms in the Fibonacci sequence approaches the golden ratio as we go to infinity. Don't worry, I'll explain that in a moment. I just want to emphasize the subtle relationship between the Fibonacci sequence and the golden ratio. I certainly didn't expect this the first time I heard about it. As promised, no previous knowledge assumed, let's begin with what is the golden ratio. The classic explanation goes like this. Imagine you got a rectangle whose height is 1 and has a length of x. What should x be, so that if we were to cut that rectangle into a square and another rectangle, the second rectangle would be similar, i.e. have the same proportions as the first. That's fairly easy to calculate. The first rectangle has proportions x to 1. By what number do you divide the height of the second rectangle, which is 1, so that you get x? The answer is 1 over x. So, we get that the length of the first rectangle x is equal to the length of the square, which is 1, plus the height of the second rectangle, which is 1 over x. Multiplying both sides of the equation by x and moving to the left hand side, we get x squared minus x minus 1 equals 0. That's a quadratic that middle schoolers can solve and find out that x is equal to 1 plus or minus the square root of 5 over 2. But we toss away the negative solution. Then we get that this number is approximately 1.618, denoted by phi, small phi, which is a Greek letter. This is the golden ratio. And now we meet our protagonist, the Fibonacci sequence, named after Leonardo Fibonacci, the Italian mathematician. It goes like this. You start out with two terms, each being 1. Some of the more veteran mathematicians might say starts with 0, but this is irrelevant to the story I want to tell. Then the sequence is defined so that each term following these two is the sum of the two terms preceding it. So the term following these will be 1 plus 1, which is 2, and then 2 plus 1, which is 3, and then 5, 8, 13, 21, 24, and 34, and so on. We name the nth term a sub n, and so the sequence is defined by a sub n plus 1 is equal to a sub n plus a sub n minus 1. This is called a recursive formula. And now we get to the main story of this video, the fact that as n gets larger and larger, eventually going towards infinity, the ratio between any two successive terms, or as we learned to call them, a sub n plus 1 and a sub n, goes towards the golden ratio, converges towards the golden ratio. Now it turns out, this is not such an intuitive fact. So we have to ask why and how to improve this. Now, here's our plan. We're gonna assume the ratio between a certain couple of terms, a sub n plus 1 and a sub n to be same. And we're gonna play with the ratio between the following succession, which will be a sub n plus 1 and a sub n plus 2 and a sub n plus 1, and so on. And we'll have to prove that the absolute value of a sub n plus 3 over a sub n plus 2 minus a sub n plus 2 over a sub n plus 1 is smaller than the absolute value of a sub n plus 2 over a sub n plus 1 minus a sub n plus 1 over a sub n. Now hang with me on this. I'm gonna explain it in a bit. We'll also have to prove that the absolute value of a sub n plus k plus 1 over a sub n plus k minus a sub n plus k over a sub n plus k minus 1 goes towards 0 for large enough k. We also have to prove that the sum of these error terms is finite and real. Now, what do we mean by the first condition? Well, we mean that if we choose a certain number n and we see the difference between the quotients a sub n plus 3 over a sub n plus 2 and the quotient a sub n plus 2 over a sub n plus 1, it will be a smaller difference than the previous difference between the preceding two quotients, meaning that the error term gets smaller and smaller and smaller as k gets larger. The second condition tells us that not only does the error terms get smaller and smaller, but that the error terms gets smaller, eventually going towards 0. The third condition tells us that we don't just need the error terms to go towards 0. We need the error terms we need the sum of the error terms to be a large finite number, meaning that the error terms go towards 0 fast enough so that their sum converges. Now, we can prove these last two facts by real analysis, but as promised, I'm not gonna get too deep into the real analysis in this video, so I'm just gonna prove the first one, and then I'm gonna explain to you how the second one is ordinarily proven. If you want to see a video proving the second and third ones, please leave a comment saying so. And now let's get to prove the first. Well, the absolute value of a sub n plus 3 over a sub n plus 2 minus a sub n plus 2 over a sub n plus 1 is smaller than the absolute value of a sub n plus 2 over a sub n plus 1 minus a sub n plus 1 over a sub n. Well, we know that a sub n plus 1 over a sub n is c, and we have our recursive formula telling us that a sub n plus 2 is equal to a sub n plus 1 plus a sub n. Then a sub n plus 2 is equal to c times a sub n plus a sub n. Factoring out the a sub n, we get that a sub n plus 2 is equal to a sub n times c plus 1. When we do the same for a sub n plus 3, we get that a sub n plus 3 is equal to 2c plus 1 times a sub n. Well, when we replace all these numbers in our original inequation that we want to prove, and divide everything through by a sub n, we get that we have to prove that the absolute value of 2c plus 1 over c plus 1 minus c plus 1 over c is smaller than the absolute value of c plus 1 over c minus c. Then, the absolute value of 2c plus 1 times c plus c plus 1 squared all over c times c plus 1 is smaller than the absolute value of c plus 1 minus c squared all over c. Taking out a negative 1 factor from the numerator of the right hand side out of the absolute value doesn't change the value, and so we're left with c squared minus c minus 1 over c times c plus 1 all in absolute values is smaller than the absolute value of c squared minus c minus 1 over c. Now 1 over c, when we multiply everything by c in the first expression by c and divide everything through by c squared minus c minus 1, we get that 1 over the c plus 1 in absolute values must be smaller than 1. So we'll have to see that the absolute value of c plus 1 is bigger than 1. If we can prove that the absolute value of c plus 1 is bigger than 1, then we can work our way backwards to prove our original expression. But it's so clear that the absolute value of c plus 1 is bigger than 1, since c is first of all a positive number, and not just a positive number. Since the Fibonacci sequence is an increasing sequence, meaning that each term is larger than the term preceding it, then c itself is bigger than 1. So the absolute value of c plus 1 is not just bigger than 1, but also bigger than 2. If you work your way backwards through these, you will find out that each error term, which is meant by the left hand side of the first expression, will not just be smaller than the previous error term, but will also be smaller than the half of the previous error term. Now we can go on to prove our second and third condition without using real analysis by saying that if you divide this error term enough times by 2, you can get as arbitrarily close to 0 as you want. And then we can see that since you're dividing by 2 or something that's bigger than 2, then the sum of all these error terms will clearly be smaller than the geometric series with an initial term of the first error term and the ratio 1/2. And since the geometric series converges for all values for all ratios less than 1, that means that the sum of all our errors also converges to a finite number, proving our third condition. Well, I'm gonna get into a bit of the nomenclature of real analysis just to show you a bit of it. We say that for all epsilon, the inverted A means for all, and that small letter is an epsilon, which is a Greek letter. There exists some M. There exists is presented by the inverted E, such that if A sub n plus 1 over A sub n is named C, and if n is bigger than m, we have the absolute value of A sub n plus 1 over A sub n minus x is smaller than epsilon. X being the perfect ratio that we want to reach at the end of the series, which is the x being the limit as n goes to infinity of A sub n plus 1 over A sub n. Now we can see that A sub n plus 1 is equal to x times A sub n, and A sub n plus 2 will approximately be equal to x times A sub n plus 1. But as n gets larger and larger, this approximation gets better and better, eventually becoming an equality. So A sub n plus 2 is equal to x times A sub n plus 1 equals to x squared times A sub n. So x squared times A sub n is equal to x times A sub n plus A sub n. Dividing everything through by A sub n, we get x squared equals x plus 1. And yes, this is the first quadratic that we encountered when we were trying to solve for the golden ratio. So x equals the golden ratio. And since x is limit as n goes to infinity of A sub n plus 1 over A sub n, that means that the ratio between any two consecutive terms of the Fibonacci sequence as n gets arbitrarily large eventually gets arbitrarily close to phi, the golden ratio. That's it. That's our proof. That's definitely one of my favorite proofs. If you'd like a version with real analysis, don't hesitate to write in the comments. If you like the video, please like, subscribe, and share it with your friends. It will help the algorithm a lot. Thank you for watching, and until next time, go Fibonacci the world.